where the radicand, what's under the radical, is not a perfect square or perfect cube or whatever the index happens to be, is always an irrational number. So irrational numbers are numbers that cannot be written as fractions. So they're decimals that go on forever and they never repeat in any pattern. So the most common irrational number that people are familiar with is pi. Right? It's a decimal that goes on forever and ever. There are people whose entire job it is to like write computer programs to find like the next digit of pi. It's kind of funny that there's a person who gets paid to do that. But because it's an irrational number, we have to use a symbol to represent it, because there's no way that I can write that number exactly, because I'd be writing forever and ever and ever. So we have to use a symbol to represent pi. And we've worked with symbols that represent numbers quite frequently and just called them variables, right? Like x is just a symbol that represents a number. And so when we have something like pi, as far as simplifying, we can kind of treat it just like a variable. And so radical expressions are the same way. So the square root of 2 is an irrational number. It's a number that I can't write exactly because it goes on forever and never repeats. So we have to use a symbol to represent it. So that's the symbol that we use to represent the number that can be squared to get 2. And so we want to think of this just like we think of a variable. So once a radical is completely simplified, the radical expression itself isn't going to change. We think of it just like a variable. So if I'm adding and subtracting, so imagine 4x plus 9x. What do I get if I add those guys? I promise it's not a trick question.
Okay.
13, but yes, you have the right idea. I had 2 students this summer who, like, really thought that 7 plus 5 was 13. Like, and they knew it wasn't, but they both would, like, consistently make that same mistake every time they had 7 plus 5. It was kind of funny. It turned into a big joke. But when I add 4 times the square root of 2 plus 9 times the square root of 2, that square root of 2 is going to behave just like the x does. So it's just behaving as, again, a symbol that represents a number. So what should I get?
13 or 2.
Mm-hmm. We just get 13 times the square root of 2. Notice that nothing happened, like I didn't like add the 2's or anything like that. Just like with the x, this part of it stays exactly the same. We're just adding the coefficients. So it can be really tempting with radicals to try to do something with the numbers underneath when we're adding. But again, once they're completely simplified, as far as addition and subtraction goes, they're going to behave just like variables. So you want to think of it like an x. We can't change that radical when we're adding and subtracting. So because of that, the only radicals we can add and subtract are like radicals, so like terms. So if I have 4 root 2 plus 3 times the square root of 5, this cannot be simplified. So we can't simplify the individual terms because 2 and 5 can't be factored. So there's no way we can simplify the radicals. And then we can't add them because they're not like terms. So I have 4 of one thing and I have 3 of something else, and so we can't add those together. That would be similar to if I had like 4a plus 3b. Because they're not like terms, we just have to leave it alone. Sometimes it looks like they're not like terms. but we can simplify to get like terms. So the first step whenever you're simplifying any expression that contains a radical is to simplify each term individually. So each radical expression you're going to simplify individually. So I look at the square root of 2, that can't be simplified because I can't factor 2. But the square root of 8 I can simplify. So we have 3 times the square root of 2 squared times 2 and then the square root of 2 squared is just 2, so this is 3 times 2 times the square root of 2. Notice that I multiplied the 3 and the 2 because this operation right here is multiplication. So when I pull that 2 out of the radical, I'm multiplying by that coefficient. So we get 6 times the square root of 2 plus 4 times the square root of 2 plus 6. Well, I have like terms now, so I can add 6 times the square root of 2 plus 4 times the square root of 2 to get what?
10 root 2 plus 6.
Good. So we have 6 plus 10 times the square root of 2. And I can't add the 6 and the 10 because those aren't like terms. So this would be like if I had like 6 plus 10x, right? I can't add. We do typically put the numerical term first, like I've done here, only because as we work through a problem, sometimes like when we write it like this, step by step, sometimes this can accidentally get a little longer and a little longer and a little longer, and like the 6 scoots under there. So typically we put any other operations in front of the radical just to avoid any mistakes with that radical symbol. Questions so far? Does this make sense? Okay, let's do a couple more. Let's do 5 times the cube root of 16y to the 4th plus 7y times the cube root of 2y minus 3 times the square root of y to the 5th. Sorry, these are cube roots. The cube root of 16. No, I don't want to do 16 again. I already did 16. Ooh, let's do 625. 250. That'll do. Okay, so first things first, we're going to simplify each term individually. So as we look at this, it's a big expression and there's lots of things going on. But you want to think of each of these as kind of just its own little problem for now. So we're going to factor our radicands. We have 5 times the cube root of 2 to the 3rd times 2, because 16 is 2 to the 4th, and then y to the 3rd times y, plus 7y times the cube root of 2y, which can't be simplified because 2 can't be factored, and then 3 times the cube root of y to the 3rd times y squared, and then the cube root of 5 to the 3rd times 2. So I'm going to take the factors that have exponents that are divisible by 3, raise those to the 1/3, and then everybody else is going to stay under the radical because it's not going to simplify. So we could have also raised 2y to the 1/3 power, but it doesn't do anything for us. We would just have to put it back in radical form, so that's why I just left it as the cube root. So plus 7y times the cube root of 2y minus 3. So we have y to the 3rd to the 1/3 power. And then again, the cube root of y squared isn't going to simplify, so I'm just leaving it as a radical. And then 5 to the 3rd to the 1/3. So, and this part of it, like, if you're comfortable just from here, just taking the cube root, like, you don't have to write it with the 1/3. So if you're like, oh, the cube root of 2 to the 3rd is just going to be 2, then you can just go straight to this step if you want to. You'll eventually get pretty quick at these simplifying if you can skip that rational exponent. But it's really helpful for organizing things at first. So times the cube root of 2y plus 7y times the cube root of 2y minus 3y times the cube root of y squared plus 5 times the cube root of 2. So far, so good? Any questions? Definitely ask for clarification if this looks different than what you guys did yesterday. But I think this is how we showed it to you. So we have 10y times the cube root of 2y plus 7y times the cube root of 2y minus 3y times the cube root of y squared plus 5 times the cube root of 2. So do I have like terms? How many like terms do I have?
Just the 2y.
Yeah, just these guys, right? And notice that when we look for like terms, we're looking for everything to the right of the coefficient. So it's not necessarily just the radical here, because we have that y as well. I can't add that 10 and 7 if one of those didn't have the y, even if the radical was the same. So when I look for like terms, I always think of everything to the right of the coefficient as being the same. That's the only way we can add the coefficient. So we have 17y times the cube root of 2y, and then 3y times the cube root of y squared plus 5 times the cube root of 2. And that's as far as I can go, because even though these guys both have y's, their radical component, their radical factor is different. And even though I have a cube root of 2 and a cube root of 2, the one on the left has that factor of the cube root of y as well. And so we can't combine those guys. So that's just all done. Let's do one more of these. How about you guys try this one? So we'll do a square root. So square root of 50 plus the square root of 32 minus 3 times the square root of 18. Let's see what you get. You can multiply radicals, so as long as the index is the same, I can multiply the square root of 6 times the square root of 2 to get the square root of 12. But I can't multiply that 6 and that 4 for any reason, because that's the square root of 6 and just the number 4. So just like when we multiply variables, so if I had x times 4x, my coefficient would remain the same, and then I'd multiply my x's to get x squared. So my coefficient is 4, and then multiplying my radicals gives me the square root of 18. And then we can simplify from there. So we'll factor. And we get 2 times the square root of 3 plus 4 times 3 times the square root of 2. It's 12 times the square root of 2. And then we don't have like terms, so we're all done. So if we are multiplying two factors that both have two terms, again, we're going to do it just like we do with binomials. So let's do 5 times the square root of 2 plus the square root of 10 square root of 5 minus 2 times the square root of 10. So again, we're multiplying two factors. They both have two terms. So just like we do with polynomials, I'm going to distribute 5 times the square root of 2 to each term in the second factor, and then distribute the square root of 10 to each term in the second factor. I feel like I didn't give myself enough space, so I'm just going to take this guy and move him. Okay, so first we're multiplying 5 times the square root of 2 times 5. And then 5 times the square root of 2 times negative 2 root 10. So a positive times a negative is going to be a negative. And 5 times the square root of 2 times 2 root 10. So I distributed 5 times the square root. Oh, this one's the square root of 5. Sorry about that. That's better. So we distributed 5 times the square root of 2 to both terms in the second polynomial. Now we'll distribute the square root of 10 to both terms in the second polynomial. So plus the square root of 10 times the square root of 5. And then positive times a negative will be a negative, and the square root of 10 times 2 square root 10. So now we'll do that multiplication in the individual terms. So square root of 2 times square root of 5 is the square root of 10. So here, one thing to keep in mind is you can multiply any two factors that are not under the radical. You can multiply any two factors that are both square roots, but you can't multiply numbers outside with numbers inside. So here, we're going to do 5 times 2 to get our coefficient. So that's 10. And then we have the square root of 2 times the square root of 10, which is the square root of 20. So again, just like with polynomials, if I had like 5x times 2x, I'd do 5 times 2 to get my new coefficient, and then x times x to get the variable factor. So same idea, I'm doing 5 times 2 to get my new coefficient, and then multiplying the radicals to get my radical factor. And then plus the square root of 50. And then again here, my coefficient is 2. And the square root of 10 times the square root of 10 is the square root of 100. Now we're going to go through and individually simplify each term. So 5 times the square root of 10 can't be simplified. I can factor 20 as 2 squared times 5. Factor 50 as 5 squared times 2. And the square root of 100 is just 10. So we have 5 times the square root of 10 minus 10 times 2 times the square root of 5 plus 5 times the square root of 2 minus 20. And I'll go ahead and multiply those coefficients. So 20 times the square root of 5. And everybody else stays the same. And we don't have any like terms here, so we can't combine anything. This 20 doesn't have a radical factor, and so I can't combine it with anything that does have a radical factor. So just like if I had 20 plus 5x, I wouldn't be able to combine those. So that's going to be your final answer. Yes?
What if you combine the two tens, that are square roots of tens, that are multiplied by each other at the end and beginning to be 3 square root of 10? Because it's the same radical, so you should be able to combine them, right?
Where?
Which square root of 10 times 2 square root of 10? Could that be combined into negative 3 square root of 10?
Right here?
No, at the very end. The last two terms in the problem.
Mm-hmm. I only see 1 square root of 10.
The very end of the problem, the negative square root of 10 times 2 square root of 10 that you turned into negative 2 times square root of 100.
On the very top.
So right here?
At the very top, the 2 that you combined into that, why can't those be combined into negative 3 square root of 10?
Oh, because I'm not adding. We're multiplying. So it's, if I had x times 2x, right, that wouldn't be 3x. It's 2x squared. So if I was doing the square root of 10 plus 2 times the square root of 10, that would be 3 times the square root of 10. But since we're multiplying, we have to multiply the square root of 10 times the square root of 10. So it can get a little tricky. We just have to be really careful about what operations we're working with. In general, a good sort of rule of thumb is that addition and subtraction change coefficients, whereas multiplication and division change exponents, or in this case, change the radical portion. So that's sort of, I mean, just like as far as things we were just talking about, like if that should be 3 root 10 or if it should be 2 root 100, because I'm multiplying, that's going to change the radical portion, not the coefficient. Other questions? Yes?
So do you not carry the -2 down to the, because in the first part it's square root of 5 minus
Uh-huh.
square root of 10.
So that's right here and right here. Right, so a positive times a negative will give me a negative. And I prefer to make that entire thing negative rather than like putting it right here. Because if I put it right there, then I'm not quite sure what I'm going to put right there, maybe. And this starts to look suspiciously like subtraction if it's between the factors. So the way I think about it is just like when I get to the point where I'm multiplying, whoops, I didn't want to erase, where I'm multiplying these two, I think, okay, I have a positive times a negative, so the whole thing is going to be negative. I write that first, and then I don't have to worry about the signs within the actual term. Does that answer your question? Other questions? Okay, let's do one more of these. So this is really similar to squaring a binomial, right? And how do we do that?
Don't you just do like square root of x plus 5 times the square root of x plus 5?
Times the square root of 5? Yes. So squaring something is multiplying it by itself, right? So we have the square root of x plus the square root of 5 times the square root of x plus the square root of 5. And then from there, we're distributing just like we did on the last problem. So the square root of x times the square root of x plus the square root of x times the square root of 5. So we distributed the square root of x to both terms in the second factor, and now we'll distribute the square root of 5 to both terms in the second factor. So the square root of 5 times the square root of x plus the square root of 5 times the square root of 5. So the square root of x times the square root of x is the square root of x squared. And we've got the square root of 5x plus the square root of 5x. And then the square root of 5 times the square root of 5 is the square root of 25. So the square root of x squared is x. And then what about the square root of 5x plus the square root of 5x? Those are like terms, so I can combine them, right? So that's tempting, but remember that once the term is simplified, that symbol is just like a variable, right? Just like back here, we didn't have the square root of 4, right? When we added those, we kept that square root of 2 and just added the coefficients.
What would be the square root of 5x squared?
So you're on the right track, but it would be 2 times the square root of 5x just because we're adding rather than multiplying. So yes, you're absolutely right. We can think of this as like having a coefficient of 1. And so it's 2 times the square root of 5x. It's so tempting to try to do something with the numbers that are underneath. You just want to always keep telling yourself if you're adding or subtracting radical expressions, once the terms are simplified, you can't change the radicals themselves. You can only change the radicals themselves through multiplication or division or factoring. And then the square root of 25 is just 5. So that's our final answer. We don't have any like terms. Questions? Okay, so last thing we're going to talk about today is rationalizing the denominator. And we're going to do the simple case today, and then we'll do the more complex case tomorrow. So the simple case is when we have just one term in the denominator, so there's no multiplication there's no addition or subtraction in the denominator. And the idea here is that if I have something like this, well, in order to simplify, I'd be like, okay, I'm going to rewrite this as the square root of 7 over the square root of 3, but neither of those can be simplified. So this is fully simplified at this point. However, we're going to take it one step further and rationalize the denominator, which means I want a number in the denominator that is not irrational. So right now, I have the square root of 3 in the denominator, and that's an irrational number, right? That's one of those decimals that goes on forever and never repeats. And I don't want that in my denominator. The reason that this all came up to begin with is a little bit antiquated. It was because people used slide rules before we had calculators. You guys ever seen a slide rule? Or heard of a slide rule?
Is it like an abacus?
It's quite a bit more advanced than an abacus, but yes, it's a tool that people used before they had calculators. It looks kind of like a ruler, and it's got all these like decimals and fractions on it. You could do anything with a slide rule. You could multiply, divide, add, subtract. You can work with decimals, fractions, pretty much anything that we can do with our calculator. Well, with maybe a standard calculator, you could do with a slide rule. The one limitation it had is that you couldn't divide by an irrational number. You could multiply by irrational numbers all day long, but you couldn't divide by them. So if I was trying to get a decimal approximation for the square root of 7 over the square root of 3, I'd be out of luck because I would have to do division by an irrational number. And so that's why people started rationalizing denominators. At this point, we do it because it helps us simplify certain expressions. So we only really do it when it's convenient, but in particular, when you do the difference quotient of the square root function, you have to rationalize. So there's a few instances where it's useful, even though the original reason that people did it is pointless because we have a calculator now that can divide by the square root of 3. So it's not that it's more simplified, but every time we simplify, we will do it so that we can practice the process. So to rationalize, I want a number that's not a radical in my denominator. And really the only way to do that is to somehow get a perfect square under my radical.
If you just put the -3 to a -1 exponent to the top, so that it's square root of 7 times the square root of 3 to the -1, so that there's nothing on the bottom.
Yeah, but the square root of 3 to the -1 is division by the square root of 3. So, like, I could write it so that there was nothing in the denominator, but in order to actually, like, do the calculation back in the day, they would still be dividing by the square root of 3. So they couldn't raise x to negative exponents because that was just division. So we're gonna just do what we've always done when we want to change the denominator. We're going to multiply by 1 in a convenient form. Well, if I want a perfect square under my radical, 9 would be a convenient choice, right? So I'm going to multiply this by the square root of 3 over the square root of 3. Because now when I do that multiplication, I get the square root of 21 over the square root of 9. And the square root of 9 is a rational number. It's just the number 3. Notice we aren't canceling anything. So this isn't like clearing fractions. We're just multiplying by something convenient so that we have a perfect square under a radical in the denominator. And so in order to rationalize the denominator when you have a single term like this, so when there's no addition or subtraction in the denominator, you're just going to multiply by whatever the radical factor is. So if I had the square root of 2 over 5 times the square root of 7, I don't have to multiply by 5 root 7 over 5 root 7 to rationalize. I just have to multiply by the irrational factor. So I would multiply by the square root of 7 over the square root of 7. And that gives me the square root of 14 over 5 times the square root of 49. Which is the square root of 14 over 5 times 7, which is just the number 35. So I could have multiplied by 5 root 7 over 5 root 7, but then I just end up canceling that extra 5 off at the end. So because that 5 is already rational, I don't really have to worry about it when I'm actually doing the process of rationalizing. Any questions? One last thing is that we sometimes rationalize when we have like a cube root. But if I multiply just by the cube root of 5 over the cube root of 5, whoops. Well, that just gives me the cube root of 5 squared in the denominator, which I can't simplify, right? In order for that to be a rational number, I have to have 3 factors of 5 under my radical, right? So I'm going to multiply by the cube root of 5 squared, because then when I multiply, in my denominator, I have the cube root of 5 to the 3rd. So whatever the index is, that's how many factors you need under the radical. So in order to rationalize if you have a different index than the square root, you just think about how to get that many factors. So then this would be over 5. Because the cube root of 5 cubed is 5. So tonight you have my math lab, and then on the homework, on the written homework, only do page 398, number 2, and number 16. So the other two, we're going to talk about rationalizing when we have 2 terms in the denominator first thing tomorrow. So that's what those other 2 are. So we'll wait on that. So just do those 2 problems. And we'll see you guys tomorrow. And I promise I'll have your homework and everything all graded tomorrow. I just got a little behind from being sick this weekend. You bet. Have a great day.
So all the test grades are
The grades are they're in my math lab.
The test grades?
Yeah, I just don't have the test to give back to you today.
I haven't been able to see the test.
Look again.
I was wondering if I could get Friday.
Yeah. Follow me. Let me get packed up and then you can just follow me back to my office.